Hello student, in this lecture we will study the behavior of the time response of different types of system like first order system, second order system by applying different types of input signal. So let's start our discussion. So see, we have seen system can be modeled in different ways, okay? So the transfer function approach is one of those types, okay? In this method, first the system is represented normally by differential equation and the Laplace transform is applied to the equation assuming zero initial conditions. Then the ratio of Laplace transform of output to Laplace transform of input is expressed as a ratio of polynomial in S and it is called the transfer function of the system. Okay. Now consider the general form of nth order differential equation is expressed in 2.15 equation. Okay, so this is the general form of nth order differential equation. Okay, here I have expressed this in equation number 2.15. Okay, so here see, choose a suffix n minus 1, a suffix n minus 2 to a0 and b suffix m minus 1 to b0 so that n equal to 1 and apply Laplace transform on both sides assuming zero initial condition. Okay, so now see here, if an equal to 1 and after applying Laplace transform on both sides of equation number 2.16 assuming zero initial condition, then the equation is like this, which I have expressed in equation number 2.17. Okay, see the equation. So the transfer function is Gs equal to Cs by Rs and this is equal to by this equation which I have given 2.18. Okay. So see, in this equation the numerator is a polynomial of degree m and the denominator is a polynomial of degree n. The degree n of the denominator polynomial is known as order of the system. We have already studied the order of the system. So the degree n of the denominator polynomial is known as order of the system. Okay. Now if n equal to 1, then the system is known as first order system. Okay, and if n equal to 2, then the system is known as second order system and so on. Okay, for all practical systems m is always less than or equal to n, that is m less or equal to n. Okay, now see the time constant form. Okay, so we have already discussed this time constant form and pole zero form. Okay, so now see here also, see the transfer function which have given in equation number 2.18, this can be represented by in this manner also. Okay, so which I have expressed in 2.18 in equation number 2.18. This equation can be represented by in this manner in the time constant form, which I have also given in equation number 2.19. If I express this transfer function equation in time constant form, if I want to express this transfer function equation which I have given 2.18 form, 2.18 equation in time constant form, then I can represent this transfer function equation in this manner, okay, where GS is equivalent to CS by RS and this is equivalent to K into TZ1S plus 1 TZ2S plus 1 like this, and this divided by TP1S plus 1 TP2S plus 1 like this, okay, where K equal to B0 by S0, okay. And this form of representing the system is called time constant form, okay. The gain K in this form is called steady state gain, okay. Now come to the pole zero form, okay. So see the transfer function equation which I have given in equation number 2.18. This can also be expressed in the following form which I have given in 2.20, in equation number 2.20, and this form is called pole zero form, okay. So in pole zero form we can express the transfer function equation like this, where GS is equivalent to K dash into S minus Z1 S minus Z2 like this whole divided by S minus P1 S minus P2 up to S minus Pn, okay. Now see here Z1 Z2 to Zm are roots of the numerator polynomial, and these roots of numerator polynomial known as zeros of the systems, and P1 P2 to Pn are roots of the denominator polynomial, and the roots of the denominator polynomial known as poles of the system, okay. And see here K and K dash are not equal, okay. We have already seen how K and K dash are related to each other in type number of the system lecture, okay. So this K and K naught are not equal, okay. Now see the denominator polynomial of the transfer function of equation number 2.19 is known as characteristics equation, okay. See the denominator polynomial of the transfer function of equation 2.19 is known as characteristics equation. The roots of the characteristics equation are the poles of the transfer function GS, okay. So what is the characteristics equation? The denominator polynomial of the transfer function of equation number 2.19 is known as characteristics equation, and the roots of the characteristics equation are poles of the transfer function, okay. Poles and zeros may be real or complex. Complex conjugate poles occur in pairs. The complex plane is used to represent poles and zeros, okay, and location of pole exhibit the stability of the system GS. So clear what is the zero, what are the zero, what are the pole, and what are the characteristics equation. So in this lecture I have discussed what are the pole, what are the zeros, and what is the characteristics equation, okay. And we will discuss the stability of the system in upcoming lecture. We have decided the stability of the system by seeing the location of pole in the S-plane. So how we will decide the stability of the system? So this we will discuss in upcoming lecture. Okay, so here this lecture I stop here. Okay.